Hello everyone, here is Khaled Omar, and in this video I'm going to demonstrate part 2 of the quality of service videos. And in this video I am going to continue the congestion management and avoidance. So the contents of this video will be only congestion management and avoidance, and we will take one tool from the congestion management and another tool from the congestion avoidance, and we will start by the congestion avoidance. And then the second tool will be related to queuing. So let's continue the tools that we demonstrated in the previous video, and we discussed in part 2 Cisco iOS tools. We started by class-based weighted fair queuing, and then we demonstrated low latency queuing or LLQ. And in this video, I'm going to demonstrate weighted random early detection as a congestion avoidance tool. And then we will discuss modified deficit round robin or MDRR as a congestion management tool or queuing tool. And in later videos, we will discuss the random early detection and weighted round robin and chained round robin, and then eventually and finally resource reservation protocol. So to define again congestion avoidance, let me first bring the pen. As a definition of congestion avoidance, it refers to the logic used when deciding if and when packets should be dropped as a queuing system becomes more congested. What this means? It means the tools that will be used as a congestion avoidance tool will be used to determine when and if packets should be dropped from a queue when the queue becomes congested to avoid this congestion. So when a queue is full, iOS has no place to put newly arriving packets, so it discards them, and this is called tail drop. As you can see in this figure, this is the queue, and it has a lot of packets, so it is full. Once it is full, there is a phenomenon called tail drop will happen. So the incoming packets will be dropped or discarded. This is called tail drop. So often when a queue fills, several packets are tail dropped at a time, given the bursty nature data packets. So tail drop can have an overall negative effect on network traffic, particularly TCP traffic. Why? Because most of the network-based traffic is TCP traffic. So when packets are lost for whatever reason, TCP senders slow their rate of sending data, the window size. When tail drops occur and multiple packets are lost, the TCP connections slow even more. So this congestion will make the network going slow down. Also, most networks send much higher percentage of TCP traffic than UDP traffic, meaning that the overall network load tends to drop after multiple packets are tail dropped. The overall throughput can be improved by discarding a few packets as a queue begins to fill. So when you discard some packets when the queue starts to fill, this can help the network not to slow down, because if tail drop will occur, the network will slow down. So we will use a tool that will randomly drop some packets when the queue begins to fill to avoid this scenario, because if the queue is full, then tail drop will occur, then and most of the network traffic is TCP, then the network will slow down. So we will use a tool called weighted random early detection. So Cisco created weighted random early detection, or WRED, specifically for the purpose of monitoring queue lengths and discarding a percentage of the packets in the queue to improve overall network performance. So the purpose of using weighted random early detection is to improve the overall network performance. And if we will not use this tool in congestion, the network will slow down. As a queue gets longer and longer, WRED discards more packets, hoping that a small reduction in offered load that follows might be just enough to prevent queue from filling. So let's discuss how WRED works. WRED uses several numeric settings when making its decisions. First, WRED uses the measured average queue depth when deciding whether a queue has filled enough to begin discarding packets. Then, WRED compares the average queue depth to a minimum and maximum queue threshold, performing different discard actions depending on the outcome. What this means? It means that first, the WRED uses a value called average queue depth, and it can be measured from the queue length, and then compares this value to a minimum and a maximum threshold. What will happen before the minimum and at the minimum and between the minimum and the maximum and after the sorry and after the maximum threshold, we will demonstrate that in this table. So the following table lists the actions. Here we compare the average queue depth versus the threshold, and here is the action, and here is the name that the WRED uses for that action. So if the average depth or average queue depth is less than the minimum threshold, no packets will be dropped. And WRED calls this action no drop. It means that the queue is not full. When the average depth value started to be between the minimum threshold and the maximum threshold, then the action will be a percentage of packets will be dropped. Why a percentage? To avoid the queue from filling. Because if the queue will keep moving, will have a lot of packets, we are trying to avoid the tail drop. Because if tail drop will occur, the network will slow down. So WRED chooses random packets to be dropped when the average depth is between a minimum threshold and a maximum threshold. And this percentage of packets that will be dropped will make the situation or the time of tail drop occurrence. If it will occur in 5 seconds, WRED will make it to be later than that by deleting a percentage of packets in that time when the average depth is between the minimum threshold and the maximum threshold. and the drop percentage increases from 0 to a maximum percent as the average depth moves from the minimum threshold to the maximum threshold. And Wred calls this action random drop. The third scenario is when the average depth is greater than the maximum threshold. So in this situation, all new packets are discarded, and this is similar to tail drop. And Wred called this action full drop. As we mentioned, when the average Q depth is very low or very high, the actions are somewhat obvious. When the average Q depth rises above the maximum threshold, Wred discards all new packets. Although this action might seem like tail drop, but technically it is not, because the actual queue might not be full, because random tail drop occurs when the queue is full, but full drop that Wred uses will occur before the queue is full, and this to avoid the time of reaching the tail drop situation. So to make this fine distinction, Wred called this action category full drop and not tail drop. When the average Q depth is between the thresholds, Wred discards a percentage of packets, and this percentage of packets are randomly chosen. The percentage grows linearly as the average Q depth grows from the minimum threshold to the maximum threshold. And in this figure, we have here the average Q depth versus the discard percentage. So when the average Q depth is less than the minimum threshold, no packets will be discarded. And then when the average Q depth starts to be between the minimum threshold and the maximum threshold, a percentage of the packets will be dropped. So when we reach the maximum threshold, all the incoming packets will be dropped. 100% of the packets will be dropped. Of the incoming packets will be dropped. So the last of the Wred numeric settings that affects its logic is the mark probability denominator, or MPD. Mark probability denominator, from which the maximum percentage of 10% is derived in the previous figure. As you saw here, 10% when the average Q depth reached the maximum threshold. And what determines this numeric value, or what we call this numeric value, we call it mark probability denominator. QoS calculates the discard percentage used at the maximum threshold based on the following formula: 1 over the mark probability denominator. So in the figure, an MPD of 10 yields a calculated value of 1 over 10, means one packet will be dropped out of 10 packets, incoming packets, meaning that the discard rate grows from 0 to 10% as the average Q depth grows from the minimum threshold to the maximum threshold. Also, when Wred discards packets, it randomly chooses the packets to discard. So the marked probability denominator is a percentage. How many packets will be dropped from the incoming packets? And this value occurs when the average queue depth is between the minimum threshold and the maximum threshold. So how wred weights packets? Wred gives preference to packets with certain IP precedence or DSP values. And in the first video of quality of service part 1, we demonstrated what are the IP precedence and what are the DSP values. When we discussed the marking field type of service, QoS, and we determined the number of bits for IP precedence and number of bits for DSP, and we listed all the values. So to do so, wred uses different traffic profiles for packets with different IP and DSP values. What are these traffic profile? A wred traffic profile consists of a setting of 3 key wred values or variables: the minimum threshold, the maximum threshold, and the mark probability denominator. And these values, we can configure them to a custom settings, and we can determine the minimum threshold and the maximum threshold and the MBD other than the default values that wred uses. So the following figure shows a case with two wred traffic profiles, one for IP precedence 0 and the second for IP precedence 3. The default minimum threshold for IP precedence 0 is 20, and the minimum threshold for IP precedence 3 is 30. The maximum threshold for both IPv0 and IPv3 is 40. So for IP precedence 0, the percentage of dropping packets goes from 0 to 10% of the packets. Means that IP precedence 0 drops more packets rather than IP precedence 3. Because as you can see here, the value for IP precedence 3 goes from 0 to 5% only before the full drop occurs, which occurs here, full drop. So the MBD for IPv0 is 10 and the MBD for IPv3 is 20. Is 5, sorry. No, it's 20 because let me check something here. It's 10 for IPv0 and it's 5, not 20. It's 5 for IPv3. Means that 5% of the incoming packets will be dropped, and this value is less than 10% of IPv0. As the figure illustrates, IPv's minimum threshold was higher than the IPv0's minimum threshold, and as a result, IPv0 traffic will be discarded earlier than IPv3 packets. Not only earlier, but also higher. So the MBD is higher for IPv3, resulting in a lower discard percentage. Based on the formula, discard percentage equal 1 over the MBD. What this means? It means that when the minimum threshold for IPv3 is higher than the IBB0's minimum threshold, the traffic for IBB0 will be discarded earlier than the IBB3 packets. This is number one. Number two, the percentage of traffic of IBB3 is lower than the IBB0. Means that for IBB0, a higher percentage of discarding packets will be occurred than IBB3. The following table lists the iOS default WRED profile settings for various DSP values. And as you know, for DSP values, which is assured forwarding, X and Y, X used for queuing, and Y for the dropping probability. But we are discussing here for WRED the dropping probability to avoid congestion. So these values are for the dropping probability only. There are no queuing. We don't discuss queuing. We discuss dropping probability. So these values that are used for the minimum threshold for the specific DSP values, and this is the default maximum threshold for all of them, and this is the MBD 10 by default for all the DSP values, and this is expedited forwarding. So when you calculate the formula, 10% will be discarded when the average depth will reach the maximum threshold. Because WRED manages drops based on the queue depth, WRED must be configured alongside a particular queue. Because in this slide we are discussing the WRED configuration. And the only one command that's used for enabling WRED is called random detect. And it is used either under a physical interface or under a class in a policy map. And usually this class is the class default. So under the policy map and class default, we enable random detect to enable WRED. The random detect DSP-based command enables both WRED and tells it to use DSCB because the default is IP precedence or precedence-based for determining the traffic profile for a packet. As we mentioned earlier, we have a default traffic profile, and we can make a custom traffic profile, configuring the minimum threshold, the maximum threshold, and the MBD. So, to change WRED configuration from the default WRED profile for a particular IBB or DSCB, use the following commands in the same location as the random detect command. As you can see here, and we will do that in the configuration on packet tracer, when you use the random detect precedence-based is the default. When you are going to configure a custom traffic profiles, you use precedence and the number from 0 to 7, and the minimum threshold and the maximum threshold and the MBD. Now you configured a custom traffic profile if you are using IP precedence. If you want to use DSCB value based on DSCB values, you can type random detect DSCB based to enable DSCB default values, or random detect DSCB and enter the DSCB value AF, X, Y, or EF, and the minimum threshold, the maximum threshold, and the MBD. So finally, calculation of the rolling average Q depth can be affected through configuring a parameter called the exponential weighting constant, or EWC. A low exponential weighting constant means that the old average is a small part of the calculation, resulting in a more quickly changing average. So this value can be configured from the command line, and a low exponential weighting constant means that the old average is a small part of the calculation and results in more quickly changing average. The setting can be changed with the following command, also it is not recommended because the default value is 9, but if you want to change this value, you can type the random detect exponential weighting constant and give it a value. The default value is 9. And if you will configure it, for example, lower than 9, the value of the average Q will react more quickly. Means that the number of bits that will be that will be discarded will be quicker than the value of 9. So let's give a WRED configuration example. And as we discussed in the previous slide, we made a simple network that consists of LAN 1, and another smaller network on the right hand side, and we call it LAN 2, and there is a WAN in between. And in this demonstration, we will consider that for R1, there is congestion in this link that we need to avoid. So we will start the configuration on R1 by using the weighted random early detection, or WRED. So let's go to the configuration. Actually, I prepared the same scenario exactly here. And let's go to R1 to start the configuration. Before we start the configuration, let me show you something. Show interface serial, and this was serial 10. Look here, the queuing strategy is class-based queuing, means that we can use WRED. If it is first in, first out, or weighted fair, you can just configure the following command, which is to enable WRED on the policy map. So let's for WRED, we will use only the class default under the policy map. So let's create a policy map and give it a name. Let's say, for example, WRED, and choose class, which is class default, because the class default is a queue that goes to congestion faster, or more quickly than other queues. So this is mainly the queue that is full and has tail drop, because the number of packets matches this class by default are all packets. So let's go to the class default and enable random detect. Before we enable WRED, it will ask you to configure a bandwidth for this class default. So we will give it a percent of 10 of the link and then enable wred. And if you go back to this, you will find it is still the same because it was by default enabled wred or use class-based queuing. If you will go to the show interface fast Ethernet 00, you will find out that the queuing strategy is first in, first out. If you want to enable wred on this interface, you can use random detect under the class default class subcommand and the policy map under the policy map. So now we enabled wred. So let's see show policy map interface. This will show you the number of packets matched in the class default, but there is something missing in the configuration to apply the policy map on the interface. So let's go to interface serial 10 service policy output, and the policy map name we call it wred, and by default the policy map is already attached, so it's, I think we didn't do that configuration before. There is already a configured policy map. So let's do it from the beginning on another router where no quality of service are configured to show you what are the default configuration and what are the new configuration that you can apply. I hope this router has no quality of service configured. Yes. So if you will go to, so we will replace the scenario from, instead of R1, we will configure on R3. So let's go to R3, and the interface is serial 11 1/1 show interface serial 1/1, because the default value is weighted fair, not class-based queuing. Class-based queuing means that wred is enabled, but here the default queuing strategy is weighted fair. If you will enable wred, it will be changed to class-based queuing. So let's configure a policy map wred class default, and then percentage bandwidth 10 or percent. Let's give it 20% of the link, and then random detect. Do show interface serial 1/1 or 0/1. Weighted fair, it should be changed. So where we configured let me do something. Show interface serial 1/1. It is weighted fair. It should be changed to class-based queuing. Show running. Yes, you know why? Because we didn't apply the policy map on the interface. Let's go to interface serial 1/1 service policy output wred. Now it will be applied, the policy map will be applied on the interface, and the queuing strategy should be changed to class-based queuing. Now we enabled random wred. If you want to see the default values, for example, let's do show policy map interface. So the show policy map interface tells you that there is wred configured on this interface and on the class default, and 10 packets are matched, and the default exponential weight is 9, and here it lists all the values, the default values for IP precedence based wred from class 0 to class 7. And as you can see here, for IPv0, the minimum threshold is 20, the maximum threshold is 40, and the mark probability denominator is 1/10 or 10, and the percentage is 1/10. So these are the default values for IP precedence. If you want to do custom configuration to change the minimum threshold or the maximum threshold or the MPD, you can go to the policy map, wred, class default, and then type random detect. First, you have to disable precedence based. Yes, break based. Once you disable this, you can enable a custom, you can enable DSCP based or configure a custom IP precedence based configuration. So let's go to random detect and then precedence, give it a number from 0 to 7, let's say 4. It will ask you to enter the minimum threshold, and for IP precedence 4 here, the minimum threshold is 28. Let's make it 29. And then the maximum threshold was 40. Let's make it 50. And the MPD was 10. Let's make it 20. Random detect on the class is required to issue this command. Okay, let's first random detect break based and then issue this command, because when you want to use DSCP based, you should disable precedence based and then do a custom configuration for the DSCP. But here we are doing custom configuration for the IP precedence, so we shouldn't disable the random detect precedence based. Let's do show policy interface. You can see here for IP precedence 4, the value changed for the minimum threshold from 28 to 29, and the maximum threshold from 40 to 50, and the mark probability denominator, it changed to 20. What this means? It means if the average Q depth is less than 29, no packets will be dropped. If the average Q depth is between the 29 and 50, 20% will be dropped. If it is more than 50, the average Q depth is more than 50, full drop will occur. If we want to configure WRED for DSCB based values, let's first disable random detect precedence based, and then random detect DSCB based. Now you will find that all the DSCB values are configured here. If you want to do custom configuration, just do random detect DSCB and let's choose AF41. Minimum threshold for the default for AF41 is 32. Let's make it 30. The maximum threshold for AF41 is 40. Let's make it 30. No, not 30. Let's make it 50. And the MBD was 10. Let's make it 5. If we will show the same command, we will find the custom configuration here for AF41. Now we finished the configuration for WRED, and let's resume the second tool, which is modified deficit round robin. Let me bring the pen. Mdrr is a queuing feature. It means congestion management feature, implemented only in the Cisco 12000 series router family. Because the 12000 series doesn't support class-based weighted fair queuing and latency queuing, Mdrr serves in place of these features. Mdrr allows classifying traffic into 7 round-robin queues from 0 to 6. And what round-robin means? It means if you have a queue here, and another queue here, and another queue here, round-robin means a packet will be served from this queue, then a packet from this queue, then packet from this queue, then go back to this queue, and so on. This is round-robin. What round-robin means? With one additional priority queue. So it uses from 0 to 6 round-robin queues plus priority queue. So when no packets are placed into the priority queue, Mdrr normally services its queues in a round-robin approach, as we mentioned here. Packets from this one and from this one and from this one, then go back to the first one. This is round-robin. This is the normal round-robin. And if there is no packet in the priority queue, normally it will work using round-robin. If some packets are in the priority queue, there will be different approach. So with packets in the priority queue, Mdrr has two options for how to include the priority queue in the queue service algorithm. The first one is called strict priority mode, and the second is alternate mode. So for the strict priority mode, it serves the priority queue whenever traffic is present in that queue. What this means? If the priority queue has some packets, the only served queue will be the priority queue. And once the packets are served, it will goes to the other normal queues from 0 to 6. So the benefit is that this traffic gets first service regardless on what's going on in the other queues. So this queue will get service first. The downside is that it can lead to queue starvation in other queues, and queue starvation means that they need service, but they don't get it because the priority queue has packets. So this can lead to queue starvation in other queues if there is always traffic in the priority queue. So in this mode, the priority queue always can get more than the configured bandwidth percentage because this queue is served more than once per cycle. So this option of Mdrr gives the priority queue the full service if it has only one packet. If it doesn't have, it can look for other packets. But if the priority queue will keeps having packets, a queue starvation will occur to the other queues. The second option is called alternate mode. It serves the priority queue in between serving each of the other queues. What this means, let's give an example here. Consider we have 5 queues are configured from 0 to 4 to 3, sorry, plus the priority queue. So it means we have 0, 1, 2, 3, and the priority queue. Let's assume that the priority queue is always have traffic inside the queue. So here is how it will be proceed. Serve a packet from 0 and then a packet from the priority queue. Then go to serve a packet from Q1 and then a packet from the priority queue. Then from B2 or queue number 2, then a packet from the priority queue. So this is the priority queue, and this is Q0, 1, 2, 3. And then a packet from Q3, and then a packet from the priority queue, and so on. The result is that queue starvation in non-priority queues does not occur because each queue is being served. But the downside of this mode is that it can cause jitter and additional latency for the traffic in the priority queue compared to strict priority mode. So, two terms in Mdrr, or modified deficit round robin, unique to this queuing method, help to differentiate Mdrr from other queuing tools. These two terms are the quantum value, QV, and the deficit. So Mdrr removes packets from a queue until the quantum value for that queue has been removed. And the QV quantifies a number of bytes and is used much like the byte count used by the custom queuing scheduler. This will be clear in the figure that we are going to give in the next slide. But before we go to the next slide, Mdrr repeats the process of every queue, which he called pass, in order from 0 to 7, and then repeats this round robin process. When repeating this round robin process, we call it a pass. So when Mdrr repeats the process of every queue from 0 to 7 and then repeats this round robin process, the end result is that each queue gets some percentage bandwidth of the link. So Mdrr deals with the custom queuing scheduler, because the custom queuing scheduler, you can change its configuration problem by treating any extra bytes sent during a cycle as a deficit. So if too many bytes were taken from a queue, next time around through the queues, the number of extra bytes sent by Mdrr is subtracted from the QV. This will be clear in the coming example. So if too many bytes what this means, it means if too many bytes were taken from a queue, next time round through the queues, the number of extra bytes sent by Mdrr is subtracted from the QV. It means the number will be decreased and the percentage will be the same. So in effect, if more than the QV is sent from a queue in one pass, that many fewer bytes are taken in the next pass. And pass means that full packets are served from the queues. As a result, averaged over many passes through the cycle, the Mdrr scheduler provides an exact bandwidth reservation. Let's show a figure here that gives an example of how Mdrr works. Let's assume that we have two queues, Q1 and Q2, and each queue has 6 packets from B1 to B6, and Q2 has from B7 to B12. The figure shows the action during the first round robin pass in the top half of the figure. This means this is the first round robin, and this is the second round robin pass. The example begins with 6 packets labeled B1 through B6 in Q1 and 6 packets labeled 7 through P12 in Q2. The arrowed lines, these lines pointing to the right, represent the choice by Mdrr to send a single packet. So when a queue first fills, the queue's deficit counter is set to the QV. The queue's deficit counter is set to the QV for that queue, which is 1500 for Q1 and 3000 for Q2. For Q1 it is 1500 and for Q2 it's 3000. So the deficit counter is set to the QV. Also, Mdrr begins by taking one packet from Q1, decrementing the deficit counter to 500, and deciding that the deficit counter is still greater than 0. Therefore, Mdrr takes a second packet from Q1, decrementing the deficit counter to minus 500. DRR then moves to Q2 because the value became minus 500, taking 3 packets, after which the deficit counter for Q2 has decremented to 0. That concludes the first round robin pass through the queues. Because as you saw here, it took two packets from Q1 and 3 packets from Q2 because of the deficit counter set for Q1 was 1500 and the deficit counter for Q2 was 3000. The end result is that Mdrr has taken 2000 bytes from Q1 and 3000 bytes from Q2, giving the queues 40% for Q1 and 60% of the link bandwidths to Q2, and this round robin process will be repeated. In the second round robin pass, shown in the lower half of the figure, this one, the process begins by Mdrr adding the QV for each queue to the deficit counter for each queue. So the Mdrr will add the QV value for each queue to the deficit counter for each one. Queue's one deficit counter becomes 1500 plus minus 500, and the end result is 1000 to begin the second pass. During this pass, Mdrr takes P3 from Q1, decrements DC to 0, and then moves on to Q2. After taking 3 more packets from Q3, decrementing Q2 deficit counter to 0, Mdrr completes the second pass. Over these 2 round robin passes, Mdrr has taken 3000 bytes from Q1 and 6000 bytes from Q2, which is the same ratio as the ratio between the QVs, which was 40% of the link bandwidth to Q1 and 60% of the link bandwidth to Q2. In other words, Mdrr has exactly achieved the configured bandwidth ratio between the two queues. As we said, 40% for Q1 and 60% for Q2. Last thing we want to mention here is the deficit feature of Mdrr provides a means that, over time, gives each queue a guaranteed bandwidth based on the following formula. The QV for Q number X divided by the sum of all QVs. So this formula guarantees a specific bandwidth for each Q, and this comes to an end of the modified deficit round robin, and we will not give an example of configuration for it. And to this we come to an end to this video. I hope it's been informative. Thanks for watching.